Asif sir, can you hear me? Asif sir. Hello, Asif sir. Hello. Asif sir.
Hi there, sir. Okay, okay. Okay, so welcome friends, welcome you all in All India Council for Technical Education AICT New Delhi sponsored Prerna scheme. Myself, Professor Asif Beg, Assistant Professor, Civil Engineering Department, Tulsiramji Gaikwad Patil College of Engineering and Technology, Nagpur, an autonomous institute and accredited NAC with A plus grade. So today in the lecture of GATE, we will learn the things on the hydrology, in which we will learn the hydrograph analysis, flood estimation and routing, reservoir capacity, reservoir and channel routing, surface runoff model. So let's start with the runoff. What is meant by the runoff? So runoff can be defined as the portion of the precipitation that makes its way towards river or ocean, etc. So as surface or subsurface flow. So either it may be of surface flow or it may be of subsurface flow or the beneath the surface flow. Whatever the runoff has been taken off in the form of river or in the form of ocean after the precipitation. So it is the part of precipitation when it flow in the form of river or in the form of ocean. Okay, so it is the portion which is not absorbed by the deep strata. So what happened actually in the precipitation, if this precipitation is happening on the land, okay, occurring on the land, so land will absorb the some amount of uh, precipitation and rest of the things will flow. So whatever the precipitation is flowing, that is nothing but the runoff. So runoff occurs only when the rate of the precipitation exceeds the rate at which water may infiltrate into the soil. So what are the portion of runoff? This is the surface runoff, groundwater flow, and the direct precipitation over the river stream. So we will see one to one. So runoff process. When the runoff occurs, a part of rainfall or precipitation is intercepted by vegetations. Some part is stored in depressions on the ground surface known as depression storage, which later infiltrates or evaporates. Some parts of the rainfall is absorbed by the soil, the amount of which depend upon the soil moisture condition at the time of percolation. Now, if the rain continues further, the water starts infiltrating or percolating to the water table, and if the rate of rainfall or rate at which the water is reaching the ground exceeds the infiltration rate and resulting surface detention, this water flow overland and joins the river, like lakes, streams, oceans, etc., and is known as surface runoff. Now, which runoff is called as surface runoff? The surface runoff is important for maximum flow, whereas the groundwater flow is important for minimum flow. Direct precipitation over the river or stream is negligible. So, for peak flow, we are generally concerned with surface runoff, and therefore we can say runoff as surface runoff. Now, what are the factors which affects on the runoff? So, first factor which is affecting on the runoff is precipitation characteristics, shape and size of the catchment, topography, geological characteristics, meteorological characteristics, character of the catchment surface, storage characteristics. Now, precipitation characteristics are it is the most important factor for runoff. Runoff depend on the type of the storm and its duration, which causes precipitation. Runoff depend upon the intensity of rainfall. More the rainfall, more will be the runoff. So this is directly proportional with the uh, uh, precipitation characteristics. More will be the rainfall, more will be the runoff. If the rainfall intensity is very less and it rains as a light shower, then much of the water will be lost in infiltration and evaporation, resulting in less runoff. If precipitation is in case of snow, then less runoff. Now, on the basis of the shape and the size of the catchment, what are the factors which we have to consider in case of runoff? So, it depends upon the size and shape and location of the catchment. Generally, more rainfall on smaller area resulting in greater runoff, and less runoff in larger catchment because due to the uniform rainfall over the entire area, thus only few tributaries of the stream feed water to a main stream during the particular storm. Now, there are two types of catchment: fan shaped catchment and fern leaf catchment. So, on the basis of the shape of the catchment, these two types of catchment are classified: fan shaped and the fern leaf catchment. So this is nothing but the fan shaped catchment. You can see here the watershed is observed here, and this is the main stream of the river. Okay, so this is nothing but the fan shaped catchment. Okay, this is spread in a very wider area, and all the tributaries are approximately of the same size, and which gives the greater runoff because the peak flood from the tributaries is likely to reach the mainstream approximately at the same time. Now, this is the fern leaf catchment. You can see here the catchment shape is like a leaf, okay, and the catchment is very steep. You can see here the area of the catchment is very less, and the tributaries are generally of the different length and meet the main stream at the regular interval. Such a narrow catchment, the peak flood intensity is reduced since discharges are likely to be distributed over a long period of time. Now, on the basis of topography, runoff depends on the surface smoothness and slope. If slope is steep, flow will be quick and less evaporation and absorption, resulting greater runoff. If the catchment is mountainous, is in mountainous area and on the windward side of the mountain, then more rainfall, resulting more runoff. Now, on the basis of geological characteristics, it is one of the important factor in case of runoff, and which includes the type of surface soil, subsoil, type of rock, and their permeability characteristics. If soil and subsoil is porous, seepage will be more, resulting reduction of the peak flood. If the surface is rocky, then absorption will be nil, resulting more runoff. If rocks have fissures and porous in nature, have lava funnel, water will be lost, resulting less runoff. So you can easily characterize or easily uh, state on the basis of the geological characteristics that in which condition the runoff will be the more and runoff will be the less. Okay, so the statement are given like if the surface is rocky, then the runoff will be more. If the surface subsoil or the soil is poorer, then the losses will be very less because it will absorb the precipitation. Okay, now, on the basis of meteorological characteristics, runoff may also be affected by temperature, wind, and the humidity. If the temperature is low and ground is saturated, then runoff will be greater. And if the temperature is high and greater, wind velocity give rise to greater evaporation loss and resulting in less runoff. Now, characteristics of the catchment surface. The runoff depend upon the surface condition like drained, undrained, natural, or cultivated. If the surface has no natural drainage, then absorption loss will be more. If more area of a catchment is cultivated, resulting less runoff. And vegetal cover reduces the runoff in smaller storms. So no vegetal cover reduction in the bigger storm. So on the basis of characters of the catchment surface, this can be other statements. Now, characteristics, the artificial storage such as dams, weirs, etc., and the natural storage such like lakes, ponds, etc., tends to reduce the peak flow, and they also give rise to greater evaporation losses. Now, what is mean by the runoff cycle that we will see? So it is a part of hydrological cycle that we have already seen in the yesterday's class, and the part between the precipitation from the atmosphere over land and its subsequent discharge through stream channel. So this is nothing but the runoff cycle, which we have already seen in the previous class. So what are the condition of runoff cycle? It is first one is end of dry period, shortly after beginning of rainfall, near the end of isolated heavy rainfall, and after the end of the rainfall. Now we will see one by one the condition of this runoff cycle. That is, first one is end of the dry period. So at the end of dry period and just beginning of heavy rainfall, all the surface and channel storage gets depleted, or we can say it dry. So expected from lakes, reservoir, and ponds resulted from the previous rains. So the only source of stream flow is the groundwater flow entering the river channel. Now the second one is that is shortly after beginning of rainfall. So shortly after beginning of rainfall and before interception, depression storage have been satisfied. The stream flow intercepted by vegetation and building can't contribute to runoff. This intercepted water is eventually returned to the atmosphere through evaporation. At the stage, a part of precipitation falls directly on the stream, which gives an immediate increment to stream flow. Now move to the third point, that is the near the end of isolated heavy rainfall. So after many hours of the heavy rainfall, virtually all depression storage and interception requirements gets filled up. The soil moisture deficiency is also satisfied to the considerable extent. Infiltration rate is near to the minimum. Similarly, the flow into the field depression is essentially balanced by overland and infiltration. Thus, at this stage, overland flow mainly contribute to stream flow. Now, subsurface flow also contributes to stream flow. Now, the fourth point is after the end of rainfall, when rain and overland flow ceases, that is, stops, the stream flow consists of only base flow and the channel storage. Evaporation takes place quite from soil moisture. Transpiration also takes place from vegetate cover. Water from depression storage also continues to infiltrate. Now, the gravity water still not drained up to the water table continues its downward journey to join water table. Now, we have a summary of rainfall runoff process. So, when a rain start falling, it is first of all intercepted by buildings, trees, and other objects, which prevent it from reaching the ground. This quantity is known as rainfall interception. Since this quantity is generally very small, it is not of much importance for intense rains, but many a time large portion of lighter rains are disposed of in this manner. The difference between the total rainfall and that which is intercepted is called ground rainfall. And when the rainfall rate exceeds the interception rate, water starts reaching the ground and infiltration into the subsoil starts. The maximum rate at which the soil in a given condition can absorb water is known as infiltration capacity. So, what is mean by the rainfall interception? What is mean by the ground rainfall? What is mean by the infiltration capacity? That we have summarized in rainfall runoff process. So, what is mean by the rainfall interception? When the rainfall is falling and it is intercepted by a building, trees, or any other object, that whatever the precipitation is occurring on that object, that is nothing but the rainfall interception. Okay, so likewise we have rainfall and infiltration capacity. Now the excess rainwater gets collected into the innumerable small and large depression existing in the basin. filling them to their overflow level. This quantity is known as depression storage. All the storage is either evaporated or used by vegetable or later infiltrates into the soil. None of it appear as a surface runoff. If after the depression storage is filled, the rain intensity P continues to exceed the infiltration capacity of the soil F, the difference appears as rainfall excess, which initially accumulates on the ground surface detention and then flow as overland flow on the basin surface before entering a stream channel. नेट बनने की है ना? The water that reaches the stream channel of a basin in this manner is called surface runoff (SRO) and direct runoff (DRO). Now, the surface runoff can therefore occur only from those storms which can contribute to excess rainfall and are simply not dissipated in fulfilling the interception, depression storage, and infiltration needs of the basin. Hence, excess rainfall minus interception minus depression storage minus infiltration. So, the sum of interception and depression storage for a basin is usually called the initial loss and basin loss or initially basin recharge. So excess rainfall can be therefore be represented as excess rainfall is equals to rainfall minus initial basin loss minus infiltration. So the sum of initial basin loss and infiltration is called as potential infiltration. So what is mean by the potential infiltration? What is the initial basin loss? What is rainfall? What is excess rainfall? What is interception? That all we have to consider while calculating this potential infiltration or the excess rainfall. Now, since the intense rains, the initial loss is very small as compared to excess rain. It is usually ignored in hydrological analysis of such rainfalls or is considered to be included in the infiltration itself. The excess rainfall is thus represented as excess rainfall is equals to rainfall minus potential infiltration. The rain that falls in the beginning of the storm before the depression storage is completely filled is called as the initial rain. And the rain that falls near the end of storm at the rate less than the infiltration capacity is called as residual rain. And the intervening period is the net supply interval. The infiltration occurring after the net supply interval is called the residual infiltration. Now, runoff and surface runoff are two different terms and should not be confused. So, what is mean by the runoff? What is mean by the surface runoff? That we have to be uh, understand. Okay. So, runoff or the discharge or the stream flow includes all the water flowing in the stream channel at any given section. While surface runoff or the direct runoff includes only the water that reaches the stream channel without first percolating down to the water table. Now, yield of a drainage basin is same as runoff, with the only difference that it is expressed over long period, million meter cube per year. Okay, and runoff is expressed for short period, meter cube per second or meter cube per hour. Now, computation of runoff. So there are three methods. First one is use of runoff coefficient, use of infiltration curves, and use of infiltration indices. Now we will see one by one. Use of runoff coefficient. The volume of runoff can be directly computed approximately by using an equation of the form Q is equals to K into P, where Q is nothing but the runoff, P is precipitation, and K is the constant depending upon the imperviousness of the drainage area. Truly speaking, this equation is not rational because runoff not only depends upon the precipitation but also depend upon the recharge of the basin. But the equation gives more and more reliable result as the imperviousness of the area increases and the value of K tends to approach unity. So this is the table number 7.3 which shows the value of runoff coefficient K. So on the type of area, the value of K is depend upon three conditions, that is flat land 0 to 5% slope, rolling land 5 to 10% slope, and hilly land 10 to 30% slope. and on the basis of type of area, it is again divided into urban area, cultivated area, pastures, or the wooded land, or the forest area, or the single family residence in the urban area. So again, we have in the case of urban area, if the 30% area is impervious or the paved, so in flat land, the value of K is zero point 0.4. In the rolling land, the value of K is 0.5. And similarly, you can see here the value is, we can see here the value for this urban area, three conditions are given, okay? And this again, the value of K is depending upon the flat land, rolling land, and the hilly land. Okay, so similarly, we have to go for this value and we have to take this value K and we have to put the value, we have to multiply this value with this P to get the runoff Q. Okay, now application of this method is where we have to use and where should be avoided. Okay, so design of storm water drains, when we have to design the storm water drains, that we have to use small water controls projects, especially for urban area where the percentage of impervious area is quite high, and where we have to avoid this method. The method of computing runoff should be avoided for rural areas and for the analysis of major storms. Now, uses of infiltration capacity curve, this is the another method. Now, infiltration capacity, which is denoted as IC curve, is a plot of the infiltration capacity against time. If the IC curve is superimposed on the rainfall hydrograph, the resultant amount will represent nothing but the runoff. So natural rains of varying intensities, sometimes below and sometimes above the prevailing infiltration capacity, results in a distortion of the capacity time curve. It is generally assumed that the infiltration capacity at any time is determined by the mass infiltration which has occurred up to that time. Now you can see here, this is the infiltration capacity curve. On the vertical axis, you can see here, this is the rainfall rate and this is the time. Okay, so as the rainfall or the runoff is shown as the in hashed line, okay, infiltration are shown in the dotted line. So this is the infiltration and this is the runoff. Okay, so as the time will increase in the initial stage, you can see here the infiltration is more, okay, but as the time goes, the infiltration is very less and the runoff is very high. Okay, so here you can see the curve for the infiltration capacity. Now the third method is use of infiltration indices. So the infiltration capacity curve already determined on the test plot cannot be applied to large basin or heterogeneous areas. At any instant in large area, the IC as well as the rainfall rate will vary from point to point. Moreover, subsurface flow or interflow will also be substantial. Since this water flow is part of infiltration, it will not normally be included in the runoff computed by IC curve determined on a test plot. Hence, runoff volumes are generally computed by using infiltration indices. Now, W index is the average infiltration rate or infiltration capacity averaged over the whole storm period, and it is given by the equation W index is equals to F by TR, where F is nothing but P minus Q divided by TR, where F is total infiltration including initial basing recharge, P is total precipitation, Q is total runoff, and TR is nothing but the duration of rainfall in hour. So phi index is defined as the average rate of loss such that the volume of rainfall in excess of that rate will be equal to the volume of the direct runoff. It can be defined the other way round as the rate of rainfall above which the rainfall volume equal to the runoff volume. So phi index can be represented graphically as shown. So you can see here the rainfall rate which is shown in the vertical axis and time TR shown in the horizontal axis, where you can see here the phi index showed here. in the dotted line. Okay, this is the fire index, which is the line in between the runoff and the infiltration. Okay, now phi index and W index will be equal for a uniform rain, but they may not be equal for a non-uniform rainfall. However, the rains which are reasonably uniform or for heavy rains, these two indices are found to be nearly equal. So in case of uniform rainfall, we have phi index is equals to W index. You can see here for the uniform rainfall, the rainfall rate and the time is given in which the runoff is shown in the hash line. Sorry, this hash line and infiltration is shown in the dotted area. So in between this line, phi index is equals to W index in the case of uniform rainfall only and not in the case of non-uniform rainfall. So in the usual case of the moderate rain of non-uniform intensities, the phi index will be somewhat higher than W index. These indices will change with a change in interception, depression storage and initial soil moisture. They will also change with the amount of precipitation. These indices are not the actual infiltration rate, but the measure of the potential basin recharge. The runoff coefficient K can be determined if the W index is known by using the equation K is equals to P minus W index divided by P, where P is nothing but the rainfall rate. Now, if you are the example like following are the rates of the rainfall for successive 20 minutes period of a 140 minutes storm. So 2.5, 2.5, 10, 7.5, 1.25, 1.25, 5 centimeter per hour are the values. Taking the value of phi index as 3.2 centimeter per hour, find out the runoff in centimeter, the total rainfall and the value of W index. So three things we have to calculate. We have to calculate the total runoff, total rainfall, and the value of W index. Now, how we have to solve this? So we have draw the equation, draw the rainfall hydrograph. Okay, so from the given rainfall rate, rainfall hydrograph is plotted to see the rain intensity patterns as shown in figure below figure. So you can see here uh, this hydrograph is shown. So for 40 this 2.5, then 10 for this till 60. Okay, then 7.5 till 80, then 1.25 till 100, then 5, then 140. So on the given data, this is 20-minute period of a 140 minutes storm. So all having 20 minutes of period. Okay, so that we have drawn here. Okay, now phi index line at a height of 3.2 centimeter is superimposed. The hashed area is calculated so as to obtain the value of runoff. Now total runoff Q is equals to 10 minus 3.2 into 2 by 20 by 60 plus 7.5 minus 3.2 divided by 20 by 60 into 5 minus 3.2 into 20 by 60. So total runoff can be calculated from the equation that we have already seen here, that is uh, Q is equals to K into P. Okay, so that we have using that equation here, and by using this equation we have calculated total runoff as 4.3 centimeter. Okay, then total precipitation can be calculated from the equation 2.5 into 40 by 60 plus 10 into 20 by 60 plus 7.5 into 20 by 60, and by putting all the remaining value into the equation you will get the total precipitation as 10 centimeter, and similarly calculate the W index, that is P minus Q divided by TR. So P is 10, Q is 4.3 and T is 140 divided by 60. So whatever will be the value you have to calculate, and you have to put the value into the equation of W index and we will get the W index as 2.44 centimeter per hour. Similarly, we are having the another example of isolated 3 hour storm occurred over an area of 120 hectares as below. So in the tabular form, it is given as the partial area of the catchment in hectare, 36, 18, and 66. Phi index, which is given in centimeter per hour, 0.9, 1.1, and 0.5. and rainfall in centimeter for first hour, for second hour, for third hour are given. Now, what we have to determine, so what is the total rainfall on the catchment in this storm that we have to calculate? Estimate the runoff from the catchment. If the phi index were to remain at the same value, what runoff would be produced by uniform rainfall of 3.3 centimeter in 3 hours uniformly spread all over the catchments. So by similar method, you can solve this example number 2. That's why I am not taking the example because we are having very short time to calculate rest of the topics uh, in 1 hour lecture. Okay, so the main important topic in the today's class is the hydrograph analysis. So a knowledge of the size and time distribution of stream flow is essential to many aspects of water management and environmental planning. A hydrograph is continuous graph showing the properties of stream flow with respect to time, normally obtained by means of a continuous strip recorder which indicates stage versus time and is then transformed to a discharge hydrograph by application of a rating curve. Now, component of the hydrographs. Hydrograph has four components: direct surface runoff, interflow, groundwater or base flow, channel precipitation. So, the rising portion of the hydrograph is known as concentration curve. The region in the vicinity of the peak is called the crest segment, and the falling portion is the recession. In most hydrograph analysis, interflow and channel precipitation are grouped with surface runoff rather than being treated independently. Now, base flow separation techniques. Several methods for base flow separation are used when the actual amount of base flow is unknown. During large storm, the maximum rate of discharge is first slightly affected by base flow, and inaccuracies in separation are fortunately not important. The separation techniques are given below. The simplest base flow separation technique is to draw a straight line from the point at which surface runoff begins. Point A in the figure below to an intersection with the hydrograph recession as shown at point B. A second method projects the initial recession curve downward from A to C, which lies directly below the peak rate of flow. Then point D on the hydrograph representing n days after the peak is connected to point C by a straight line defining the groundwater component. The choice of n is based on the formula n is equals to a raised to the power zero point 0.2, where n is nothing but the time in days and a is the drainage area in meters square. Now, base flow separation technique in the continuation, we are in the third part, which is third procedure employs a base flow recession curve that is fitted to the hydrograph and then computed in the time decreasing direction. From the diagram shown, point F where the computed curve begin to deviate from the actual hydrograph and the end of the direct runoff. The curve is projected backwards arbitrarily to some point E below the inflection point, and its shape from A to E is arbitrarily assigned. Now, fourth widely used method is to draw a line between A and F. We have to note one thing that all of these methods are approximate since the separation hydrograph are partly subjective procedures. Now, time base of the hydrograph. The time base of hydrograph is considered to be the time from which the concentration curve begins until the direct runoff component reaches zero. An equation for the time base may be written as Tb is equals to Ts plus Tc, where Tb is the time base of the hydrograph, Ts is the duration of runoff producing rain, and Tc is time of concentration. The hydrograph time base related to both storm and basin characteristics is a basic element of unit hydrograph theory. Unit hydrograph. So unit hydrograph represents a unit direct runoff for specified duration over the entire watershed. So what is the concept behind this is we have to divide the hydrograph into unit. Subtract base flow from each segment and divide the answer by the total hydrograph. So what is meant by the time lag of hydrograph? So what is time lag? The difference in the time between the center of mass of effective rainfall and the center of mass of runoff produced. So lag is influenced by the shape of the drainage area, the slope of the main channel geometry and storm pattern. Now we have the tutorial question on unit hydrograph. So actual discharge for a flood hydrograph passing the point of concentration for a 600 hectares drainage basin are given below. The flood was produced by a uniform rainfall of 5 cm per hour, which started at 9 a.m. and abruptly ended at 11 a.m. and resulted in 5 cm of direct surface runoff. The base flow prior to, during, and after the storm was 100 centimeter cube per second. So, on the basis of this time, the discharge are taken. Okay. Now, at what time did direct surface runoff begin and cease? And derive the 2-hour unit hydrograph ordinate for each time listed. Now, how we have to solve this, that we will see. So, direct surface runoff began at 9 a.m. and ceased at 6 p.m. So, time we will write in 8, 9, 10, 11, 12, 1 p.m., then 2, 3, 4, 5, 6, 7. And flow in centimeter cube we have write as per the given. Then uh, then base flow we have right, and then direct runoff. Okay, so 2-hour unit hydrograph should be divided with respect to 5. Okay, so all the direct runoff, when we are getting this direct runoff as 200, we have divided with respect to this 5. So we will get the 2-hour unit, that is 40. Then this is 400 divided by 5, 80. Then this is 600 divided by 5, this is 120. Then 700 divided by 5, that is 140. So similarly, we will get the 2-hour hydrograph from the given question. Now, what are the components or the part of storm hydrograph? So on the vertical axis, you can see here, this is the discharge is given, okay, and on the horizontal axis, the time is given. So this is nothing but the single peaked hydrograph resulting from the isolated storm. Okay, now as the time is increasing, this is the peak point, and this is the number of days. Okay, so AB, where you can see here, this is AB. This AB is nothing but the groundwater flow. BC, this portion BC is nothing but the influent stream flow. Then CD, this portion is nothing but the overground flow area. Now ABCD direct runoff, this A, B, C, D. This portion is nothing but the direct runoff. Okay. Now this is at the point of E. This is nothing but the point of inflection, and at this inflection, this hatch line showing the recession. Okay. So flow due to the channel storage. So this is nothing but the recession. So moving toward the flood routing. So what is meant by the flood routing, which gives the some information on the movement of flood wave along a river reach, takes into effect the storage within a river reach or channel system, always done in river system and reservoir. The two methods used for routing are hydrologic method and the hydraulic routing. So what is meant by the hydrologic method, which is uses the routing equation and uses the continuity equation. So continuity equation, that is the mass of the conservation of mass of the conservation in the fluid mechanics. We have already seen that in the yesterday's class, that continuity equation we have already seen. So what is continuity equation? Q is equals to area into velocity. So hydraulic routing is also included this method continuity equation. Q is equals to A into V, and dynamic equation V is equals to 1 divided by N R raised to the power 2 by 3 and S raised to the power 1 by 2. Now what is Now, hydrologic river routing are all found upon the equation continuity in the form I minus O is equals to ds divided by dt, where I is inflow and O is outflow, and where ds divided by dt is the rate of change in storage within the reach. So similarly, I1 plus I2 by 2 is equals to O1 plus O2 by 2 plus S2 minus S1 divided by delta T. Now, Muskingum method, we will move towards the Muskingum method now. So, storage in a stable river reach can be expected to depend primarily on the discharge into and out of a reach and upon the hydraulic characteristics of the channel section. The storage within the reach can be expressed in the form S is equals to B by A into XL raised to the power m by n plus 1 minus x bracket into O raised to the power m by n, and constant A and n reflect the storage discharge characteristics and B and m mirror the storage volume characteristics. The factor x defined the relative weight given to inflow and outflow within the reach. The method assumes that m by n is equals to 1 and let b by a is equals to k. Then 1 becomes s is equals to k into xl plus 1 minus x into o. So this is the equation number 2. Now k is nothing but the storage time constant for each reach. X is the weighing factor that varies between 0 and 0.5 for a given reach. Now, Muskingum method, in the continuation, application of the equation has shown that k is reasonably closest to the travel time within the reach and x will average about 0.2. If k and x are known, routing procedure begins by dividing time into a number of equal increments del t and express equation 1 in infinite differences form. The routing time delta is normally assigned any convenient value between the limits k by 3 or k using subscript 1 and 2 to denote the beginning and the ending times of the interval delta. The storage change in the river reach during the routing interval is S2 minus S1 is equals to K into X into L2 minus L1 plus 1 minus X into O2 minus O1. Now substituting into L1 plus L2 by 2 minus O1 plus O2 by 2 is equals to S2 minus S1 by 2 results in Muskingum routing equation, and that is equals to O2 plus C0 I2 plus C1 I1 plus C2 O1. Now there C0 is nothing but minus Kx plus 0.5 del T divided by K minus Kx plus 0.5 del T. C1 is equals to K into K plus zero point 0.5 del T divided by K minus Kx plus 0.5 del T, where C2 is equals to K minus Kx minus 0.5 del T divided by K minus Kx plus 0.5 del T. So what note we have to remember is K and del T must have the same time units and the coefficient must sum up to 1. Now since I1 and I2 are known for vary every time increment, routing is accomplished by solving equation for successive time increment using O2 and O1 for the next time increment. Now these are the tutorial questions given, so we won't go into much detail for solving the questions at this moment because we have very restricted with the time. So we will stop here and we will see the questions which can be solved, which is asked in the gate examination, and we have solved that questions by using the equation which we have learned today. Okay, so that we will see. So I hope at this moment you have all understood about the unit hydrograph, what is mean by the different types of routing and many other things. Okay. Now moving towards the next we will try to cover in 10 to 15 minutes about the question asked in the gate examination. What is mean by what types of question is asked on this unit hydrograph, or the routing, or the topic which we have covered in today's class. So let's begin with the question which we have stopped yesterday. So question number, I think 4 or 5 we have covered. Okay, so question number 6, that is the plan area of the reservoir is 1 kilometer square. The water level in the reservoir is observed to decline by 20 centimeter in a certain period. During this period, the reservoir receives a surface inflow of 10 hectares. I am just zooming it out because last time I have received the feedback from your side that the screen is not visible properly. So that's why I'm just increasing the or the zooming it out. Okay, so during the period of reservoir receives a surface inflow of 10 hectares meter, and 20 hectometers are subtracted from the reservoir for irrigation and the power. The pan evaporation and rainfall recorded during the same period at a nearby meteorological station are 12 centimeter and 3 centimeter respectively. The calibrated pan factor is 0.7. The seepage has from the reservoir during the period in hectometer is, so seepage we have to calculate. The options are given as 0, 1, 2.4 and 4.6. So inflow of water is given as 10 into 10 raised to the power 4 meter cube. Outflow is given as 20 into 10 raised to the power 4 meter cube. Rainfall is given as 3 centimeter. Volume of rainfall can be calculated from 1 into 10 raised to the power 6 into 3 by 10, 3 by 100. So we will get the volume of rainfall as 3 into 10 raised to the power 4 meter cube. Now evaporation is given as 0.7 into 12 for 12 hours, so 8.4 centimeter. Now volume of evaporation 8.4 divided by 100 into 1 into 10 raised to the power 6. So you will get the evaporation volume as 8.4 into 10 raised to the power 4 meter cube. Now net decrease of the volume is 10 minus 20 plus 3 minus 8.4 into 10 raised to the power 4 meter cube. So we will get the net decrease of the volume is minus 15.4 into 10 raised to the power 4 meter cube. Now, in terms of depth, if you have to calculate, you have to take the net decrease of the volume divided by 10 raised to the power 6. So you will get the value as 0.154 meter, and you are converted into centimeter, it will be equals to minus 15.4 centimeter. Now, what is the observed decrease of the level is 20 centimeter. So 20 minus 15.4, you will get the 4.6. So option D will be the right answer for this. Okay. Now, moving towards the next question, which is asked on average rainfall of 16 centimeter occurs over a catchment during a period of 12 hours with uniform intensity. The unit hydrograph is equals to that is having unit depth is equals to 1 centimeter, which is having duration 6 hours. Of the catchment rises linearly from 0 to 30 cumex in 6 hours, and then falls linearly from 30 to 0 cumex in the next 20 hours. So fire index of the catchment is known to be 0.5 centimeter per hour. Base flow in the river is known to be 5 cumex. Peak discharge of the resulting direct runoff hydrograph shall be. The options are given as 150 cumex, 225 cumex, 230 cumex, and 360 cumex. So the rainfall in the first 6 hours is equals to 8 centimeter, and the rainfall in the second 6 hours that is also 8 centimeter. Now, if you plot this diagram for 6 hours, that is 1 centimeter, so fire index is equals to 0.5 centimeter per hour. In 6 hours, the losses we have to calculate as 6 into 0.5, 3 centimeter are the losses. So net uh, we will receive 8 minus 3, that is 5 centimeters. So the direct runoff on the hydrograph will be equals to 5. Now the total at 12th hour will be 75 plus 150 is equals to 225 meter cube per second, and the base flow will be equals to 5 meter cube per second. The total flow will be 230 meter cube per second. So option number here 230 C option will be the right answer for this question. Okay, so you can see here in the numerical part, whatever the question asked in the gate examination, that is all are required the equation behind it. Okay, so if you remember the equation which we have covered in the presentation, you will lead to, or you will success to get the 2 marks directly. Okay, so an average rainfall of 16 centimeter occurs over a catchment during a period of 12 hours with uniform intensity. The unit hydrograph unit depth is equals to 1 centimeter, duration is equals to 6 hours of the catchment rises linearly from 0 to 30 cubics in 6 hours and then falls linearly from 30 to 0 cubics in the next 12 hours. Phi index of the catchment is known to be 0.5 centimeter per hour. Base flow in the river is known to be 5 cubics. Area of the catchment in the hectare is, so area of the catchment we have to calculate in the hectare. So A into 10 raised to the power 4 into 5 by 100. So you will get the value as 9720. So C option will be the right answer for this. Now, yes, this question we have covered already in examination in the presentation itself. Okay, so the rainfall during the three successive 2 hours period is 0.5, 2.8, and 1.6 centimeter. The surface runoff resulting from this storm is 3.2 centimeter. The phi index value of the storm is, so phi index value we have to calculate. So already we have seen in the presentation itself that total rainfall in 6 hours calculated by summing up zero point 0.5, 2.8, and 1.6. We are getting as the value of total rainfall in 6 hours is 4.9 centimeter. Now surface runoff is 3.2 centimeter. So the phi index will be equals to 1.2 plus phi minus zero point 0.5 into 2 is equals to 3.2. So the value of phi is equals to 0.3 centimeter per hour. So likewise, you have to calculate the phi index, or sometimes it is to be asked in the examination to calculate the W index. That is also we have seen in the presentation. Now the intensity of the rainfall and the time interval of a typical storm are, time interval are given and the intensity of the rainfall in per minutes are given. Now, what we have to calculate the maximum intensity of rainfall for 20 minutes duration of the storm. So that we have to calculate. So maximum rainfall for 20 minutes we will calculate from adding this 0.7 with 1.1 and by multiplying this with 10. So you will get the value maximum is 37. You can see here maximum value is 37 in 20 minutes. So 37 by 2, that is 1.2, 1.85 per minute. So 1.85 per minute, that is this value. B option will be the right answer for this. Now during a 3-hour storm, uh, it was observed that all the obstructions other than infiltration are negligible. The rainfall was idealized as 3 1 hour storm of intensity 10 per hour, 20 per hour, and 10 per hour, respectively. And the infiltration was idealized as a Horton curve. F is equals to 6.8 plus 8.7 exponential minus T. F in the per hour and T in the hour. What is the effective rainfall? So, to calculate the effective rainfall, we are having this equation. As this topic is not we have covered in the gate syllabus, because this was not the today's topic, but still we will try to solve this numerical by using the infiltration limit having 0 to 3 f t into dt. So by putting all the value of f and t into the equation by and derive this equation, differentiate this equation with dt, you will get effective rainfall as 11.33. So option number B will be the right answer for this. So you can see here we have multiple questions which are asked in the gate examination, and only you have to remember the equation, the condition of the rainfall, or where you have to calculate the phi index or W index, or where you have to calculate the unit hydrograph. So that thing that I think here we can stop here, and we will meet in the next class for with the new topic. Okay.
shall I end it?
Okay, sir.